An electrolyte will conduct electricity.
A strong electrolyte will completely dissociate when dissolved in water.
A weak electrolyte will only partially dissociate in water.
A non-electrolyte will not dissociate when dissolved in water.
Our first objective: determine which samples are strong electrolytes, weak electrolytes, and non-electrolytes.
The second objective of this experiment was to observe the effect of concentration, which is defined as the quantity of solute present in a given quantity of solvent or solution, of a strong electrolyte on conductivity.
Our third objective: observe the neutralization of a strong acid, strong base titration.
Hypothesis 1 for Part A describes the samples being tested. Strong acids, salts, and strong bases will light the light bulb with the conductivity tester. The sample that is sugar will not light the light bulb when tested with the conductivity tester.
Hypothesis 2 was for Part B. Hypothesis 2 was the non-diluted, which is a more concentrated, solution of HCl will have the brightest light bulb, indicating the strongest conductor.
Hypothesis 3 for Part C, the acid-base titration will be neutralized when there are equal parts of HCl and NaOH.
The main formula used in this experiment is M1 times V1 equals M2 times V2.
Beginning with Part A, we first placed 80 milliliters of the sample solution in a 100 millimeter beaker and placed the conductivity tester inside. We did this conductivity test on 6 different sample solution, which were NaCl, sugar, HCl, NaOH, NH3, and CH3COOH. Between each test, we made sure to wash the electrodes from the conductivity tester when changing the solutions. We recorded our results based on the brightness of the light bulb. From these records, we could then determine which solutions were strong electrolytes, weak electrolytes, and non-electrolytes.
After completing the conductivity tester with our 6 sample solutions, we determined that sugar is a non-electrolyte. Our strong electrolytes were NaOH, HCl, and NaCl, and our weak electrolytes were CH3COOH and NH3.
For Part B, we prepared 100 milliliters of 0.10 molarity HCl and 0.010 molarity HCl solutions. To do this portion, we filled 10 milliliters of 1 molarity HCl in a 100 milliliter graduated cylinder, and then added the rest with water until 100 milliliters. We tested this solution. Using this prepared sample, we took 10 milliliters of the 0.10 molarity HCl in a 100 milliliter graduated cylinder and added the rest with water until 100 milliliters. This process diluted the HCl sample so that we could determine which concentrated solution produced the most light with the conductivity tester. We used the previous sample from Part A to do our comparison. With these 3 samples, we could rank them from brightest to dimmest.
In Part B, we gathered in order from brightest to gradually decreasing darkness that the hydrochloric acid was brightest at 1 molarity, moderately bright at 0.10 molarity, and almost indistinguishable with barely any brightness at 0.01 molarity.
For Part C, we prepared another HCl solution, which was 5 milliliters of 1 molarity HCl plus 45 milliliters of water plus 5 drops of phenolphthalein in a 100 milliliter flask. We then used a 10 milliliter graduated cylinder and placed 10 milliliters of 1 molarity of NaOH inside. Now with these 2 different solutions, we added 1 milliliter of NaOH to the HCl solution 1 milliliter at a time so that we could observe the brightness of the light. We recorded our observations, the color of the solution plus the light after each milliliter added.
After completing Part C, our results were 5 milliliters for the volume range of NaOH at least brightness or darkness, and 5 milliliters for volume of NaOH when solution turns pink, and 5 milliliters for the volume of NaOH calculated.